We discover an expanding universe. If we're expanding, it is vast in every metric we've ever established for it. There are things that are vast in size, in temperature, in speed.
Just to get a feel for that, take a tree and expand it to be the size of the observable universe. Then the Planck scale would expand roughly to the size of an atom. So the Planck scale is to an atom as a tree is to the universe.
This very quickly leads you to have even greater existential dread, because if you run the movie backwards, it gets to a point which seems quite catastrophic, where these galaxies are literally on top of each other, and eventually you're kind of imagining something that's so dense that you have to start thinking of it as hot, soupy, and chaotic.
The reason why you can't put quantum mechanics into it, it already seems to have quantum mechanics embedded in a deep and subtle way that Einstein himself didn't recognize.
Oh, please do tell them, because my edible just kicked in and this is fascinating. You can't put something into something
if it's already
where the thing is there.
That's it.
We just don't know where it is inside of that thing, but once we find it in there, we're gonna be like, yo, that's where it is. And be like, I told you not to put it in there. It was already in there. That's simple, it's elegant, it's profound, it's amazing.
I agree.
So maybe it's not the photon being pulled, maybe the space itself is being warped and the photon is like surfing on the space. And so it's just like, yeah, man, this wave is awesome. And so you see it curve, right? But if that's the case, why can't it escape a black hole? Because does that mean that the space inside of a black hole is being folded in so that even the photons can't get the out?
Yeah, essentially.
All right. Who's that out there with the sparkly?
But I want to be Morpheus, he says. You can't be Morpheus. I said, why not? He said, because I'm Morpheus. It's a stupid conversation. You ever hear those guys that sing in that really, really low voice? They're like,
Basso profundo?
Basso profundo.
Basso profundo.
It's like you can almost see the vocal cords vibrate.
Oh my God, that's pretty good. Oh, look, I'm live. Hi, Janna. Nice to meet you.
Number one.
Hey, man. Oh, the crowd is ready for it. I got you. No, I don't do the back. I sit on it, and I got a butt sticking out like this. So this is where, in 1920, we didn't know if there were other galaxies.
Oh, wow.
Yeah, I mean...
We thought we were the main character the whole time.
The Milky Way was the universe.
Oh.
Yeah. Immanuel Kant, even in the 1700s, imagined that some of these fuzzy things were island universes.
I can't hear his name without me. I'm so sorry.
Immanuel Kant.
Stop saying it. Gosh, stop.
Okay. Island universes?
I think so.
You think so? I have uncommonly fast reflexes.
I was wondering maybe
Okay.
He's got to be every
They're uncommonly fast. Okay. Too slow.
What do you see? Yeah, okay, I just wanted to know. I want to double check it now.
He's getting a knuckle. There. So you're pretty fast. Let me say.
Yeah. He was like, you're not getting any chances.
Oh man, all right.
Okay. Nice. That was nice.
Well, you got it. So before we begin, I didn't know this until today, that the two of you are actually current collaborators on some research. Could you just highlight what that is? What are you doing?
I mean, Brian and I have been working together for years.
Yeah.
Mostly, we've been thinking about extraspatial dimensions and different cosmological implications for theoretical physics, hiding some dark energy and some extra dimensions.
As one does.
As one does, yes.
You're thinking about higher dimensions.
Yes.
Because
I mean,
the 3 plus time dimensions are not enough for you.
well, even Einstein, when he started working, wondered why 3. I mean, it's a curious question. Once you start...
Well, it's a magic number.
Yeah? Is it
Thank
your
you.
favorite number?
Wait.
Those are Schoolhouse Rock people right there.
They count to 3.
They got it right away.
Okay, but how many dimensions are there, really?
We don't know, but certain theories tell us that it could be much more than the ones that meet the eye. So it could be as many as 10 or 11.
Oh, like gender.
But
I said it, and now I'm getting arrested.
you just make up other dimensions. I mean, it sounds like you're pulling it out of your ass. I mean, sorry.
Yeah, it's all.
He didn't deny that immediately. That was, I'm worried about this. Okay.
Well, partly it is, but it is also deep mathematical reasons that lead us to these ideas.
Yeah,
So-
and we figure if nature can try some experiments, she will. So every
Okay.
possibility might actually happen.
Okay.
So we're just exploring.
All right.
How much weed do you guys smoke?
All right. So
Complete silence.
the microscope and telescope were invented 400 years ago. And like I said, they take us to the grandest visions of our understanding of our place in the universe and the tiniest visions that also give us an understanding of our place in the universe. And so those first steps were magnified at the dawn of the 20th century, especially through the 1920s. And so let's start out with the large, and we'll end with the small, okay? So let's go back to the roaring 20s. Let's just do that. And here's something that it's hard to even believe that just 105 years ago, we didn't know if there were other galaxies. We just thought all the stars in the night sky, the Milky Way, was the entire universe. There was we weren't given reason to think anything else. There were these fuzzy things in the sky. Okay, they're just fuzz. We call them nebulae, which is Latin
For fuzz.
Yes, thank you. So
So we just thought it was just space lint.
yeah,
Just,
yeah.
Sure.
But some fuzz lint base. Now you're messing. Nebulae. Some nebulae were
Nebulae.
spiral shaped, and others were irregular. And the irregular ones were found in the plane of the galaxy, whereas the spiral ones were in every direction you looked.
Interesting.
So that was odd. It was a first thing. Well, maybe we can unpack this and figure out what's going on. So there was a famous debate, took place in 1920, at the hosted by the National Academy of Sciences, between Heber D. Curtis, yes,
Unfortunate name.
he had that name, and Harlow Shapley, soon to become the director of the Harvard College Observatory. And Heber Curtis was director of the Allegheny Observatory. Two very different.
Yeah, I'm going to say one of those sounds more expensive.
All right, so they debated whether these spiral things were other galaxies. With a term coined by Immanuel Kant in the 1700s, who thought about this, philosopher. Yes, Chuck?
Brian did it to me, man. I'm sorry.
What did Brian do to you?
Because he knows I can't hear the name Immanuel Kant without being 12 years old.
Okay.
I'm so sorry.
Okay. So he's a philosopher, deep-thinking philosopher. He looked up and he saw these spiral objects, and he thought of them as possible island universes.
Oh, that's pretty cool.
That's
An island
beautiful.
universe.
That's beautiful.
Yeah.
That is.
But we didn't have evidence to say that, to support it, but it was a deep idea at the time. So there they are, they debated this, and
But based on what evidence? Just hot taken?
they're scientists.
Okay. All right.
Which means,
Sometimes we have rose-colored glasses towards the past. as
yes,
one
I get
might
it,
say.
I get it.
Yeah.
So here's how it works. Two scientists argue, there's a pact implicitly signed before they even begin, which is either you're right and she's wrong, you're right and he's wrong, or you're both wrong. They know this going into the conversation.
It's Nerd Thunderdome.
So,
2 scientists enter. 2 scientists leave, but one's a little embarrassed.
pay-per-view Saturday night.
Yeah.
So,
Yeah.
so here's
This is their Tyson, Jake Paul. Real kind of throwdown.
So let's go to the Harvard fellow.
Yeah.
Because you can always tell a Harvard man, but you can't tell him much.
Oh, got it. Oh, so they were insufferable back then as well. Got it. Were they also like, I went to school in Boston?
Boston.
Like, fuck you. Just say it. Just say it.
So
Say it. You know? I don't know.
all right. So
Go ahead, back to the.
here's what happened.
Let's merch.
Shapley was heavily invested in the entire night sky being the whole universe and the Milky Way. And he had evidence at the time from a fellow astronomer who had looked at the spiral nebulae and claimed that he found them having moved on the sky. Now, if you're really, really far away, that's essentially impossible to measure. But if you're close up and you're moving, you can see that movement, okay? Things that are close to you. So the example here is, if I see a plane moving across the sky, and then I see a bird moving at the same angle, I don't conclude that the bird is going 600 miles an hour. The bird is much closer. So at much lower speeds, I can see it cross my field of view. So, because it's closer. That evidence suggested that the spiral nebulae were nearby, and he bet on that horse, but it was the wrong horse. He was doing what a good scientist will do. He took the data, put his confidence in the data. It was later shown that the data he was basing his argument on was false. It could not be verified by the work of other scientists. And in fact, no, the spiral nebulae had no motion across the sky. And so Shapley was just wrong. We would later show that he's wrong. And what puts the nail in the coffin? 1923. Edwin Hubble.
Oh, the man.
Hubble was a person before he was a telescope. Yeah.
I thought he was born a telescope.
Born a telescope.
Yeah, just like when you're a kid, you're like, of course. There was Ninja Turtles, and they were birthed. And
Yeah, there it is. There it is. So he had an idea based on evidence, and it turned out to be wrong because the evidence was flawed. So there's some lessons there. All right? And if one scientist has one bit of evidence, you don't alert the authorities yet until there's confirming other experiments to do so.
That is what the peer review is all about.
That's
right?
peer review is all about.
And by the way, for anybody who wants to know, scientists are haters. Okay, that is what they do. You come up with something, and somebody goes, "I call bullshit," and then it's on. Then it's just on.
Wait. So Neil, a peer review to us non-scientists is basically it's scientific group chat where you present your take or information, and
Yes.
the 17 other friends that are in the group chat get to be like, bullshit.
And Shapley had a green bubble in the chat. That's
goddamn, what a horrible life to live. He was the one green.
He was the one green.
Surrounded by blues.
Yeah, and if you have an idea and it's shown to be wrong, then it's just wrong. In fact, Einstein, after his relativity, which we'll get into in a couple of minutes, that was hard to accept by people, right? It was, it was hard. It was very counterintuitive. Someone came up with a work saying 100 against Einstein. 100 against Einstein. And then he's rumored to say what after that?
Let's say I just learned this anecdote, but he's rumored to have said, why 100? If I'm wrong, 1 would have been enough.
Wow.
Yeah.
It's pretty great.
Yeah. And believe me, I've been married for 27 years. That is right.
Okay, so here's what happened. So Edwin Hubble is curious about these spiral nebulae, and he finds a star in them that matches a kind of star that's not in a nebulae, that's just sort of nearer by than that star. And it's a very specific kind of variable star, named after the very first of its kind, Cepheid variable. The first of its kind was found in the constellation Cepheus. And so that's how we categorize types of variable stars. The first one in a constellation, all the others, no matter where you find them, are that variety. Found a Cepheid variable there. And what was tell us what's special about the Cepheid variables.
Well, they have a very predictable property where their luminosity, how bright they shine, is related to a sort of oscillation. And so you can tell that you're looking at precisely one of those. It's
Right.
very easily identifiable.
If you get the luminosity out of it,
Yeah.
then you can say, I can see the period vary.
Right.
And based on that period, I know how bright it should be.
How bright it should be. So it's as though you knew your light bulb, right?
Yeah.
You can tell if you have a very bright light bulb far away or a very dim light bulb up close.
Right. How can you distinguish the two?
And how do you distinguish the two if you know nothing about the light bulb? But if you know everything about your light bulb,
Yes.
you know exactly what it is, then you can say, oh, I know this light bulb, so I know exactly how far away it is.
So he says this star is of this particular luminosity, and the only way it could be that dim is if it is far
away. You know, everything happens in space, and space is happening in space-time. In the 4 dimensions of space-time, there can never be a time without a place, and vice versa. If I say meet me, you will need to know where and what time to make that happen, regardless of the place throughout the entire universe. Well, how would you like to give the gift of space-time? Suppose I told you you could mark any occasion with a beautiful physical representation of its corresponding space-time. Well, thanks to our friends at Under Lucky Stars, you can do just that. Under Lucky Stars makes beautifully designed star maps that show the unique alignment of the stars in a place and date chosen by you. Whether it's a birthday, an engagement, wedding, or when you first met, the stars never look the same twice. Each star map can be personalized with your unique title and footnote. Now, I have 3 children, and I gave each one of them a birthday star map. Each one has the same message. This is the sky under which Morgan entered the universe. This is the sky under which Aiden entered the universe. And this is the sky under which Charlie entered the universe. And they love it. And so will your mother, brother, sister, father, wife, child, best friend, or even your boss, you know, if you're that kind of employee, because you're giving them the most unique commemoration of a significant life event that they will always cherish. So don't wait. You can even go super meta and give them a star map of the day you gave them a star map. All right, okay, maybe I'm prone to being a little extreme, but perhaps you'll just start with an important date. Go to underluckystars.com and immortalize the happiest moments of your life. That's underluckystars.com. And now, back to the space-time that is the show.
But it's important to know what he actually meant by that, because Hubble himself never was convinced that these were actually other galaxies. He proved that there was something beyond the outskirts of our galaxy. We knew our galaxy about 100,000 light years across. His analysis showed this to be 900,000 light years. We now updated it to 2 million light years. But Hubble was so conservative that he was unwilling to then say, this is an island universe, this is a galaxy in its own right.
What an idiot.
Wait, what's the difference, just from a space real estate standpoint, what's the difference between an island universe and a galaxy? What are we talking?
They're
Condo,
poetically identical.
house?
They're the same.
They're the same.
Poetically identical.
Yeah.
Got it.
Yeah.
Okay.
Yeah, because if our galaxy is our universe and there's another galaxy, then you get to call that a universe. Except, once we see the full breadth of it all, we got to reallocate how we use the word universe. Because it's universe. One in
One verse.
Right. But we're in the multiverse. Spider-Man. We're in the.
We'll get to that.
Okay.
Yeah. We'll get to that.
All right.
Minus the Spider-Man, but we'll
You didn't like the second one. I thought it was great.
So, Janna, we're reeling from the fact that we are not the universe. We're just a part of a universe. And then a few years later, Hubble discovers that these spiral nebulae are in motion, body and soul. So what's going on there?
Yeah, so once he's starting to be able to use these Cepheid variables and these standard candles to get a strong sense of how far away things are, he can start to do that kind of mapping out the local environment, what we have right nearby, and then also galaxies further away, these little smudges on the sky. And he begins to catalog not only that there are other galaxies around us at great distances, but there also seem to be receding away from us, largely, predominantly.
Yeah, and so he makes a plot.
Makes a plot. So this is very strange. I mean, you're looking at all of these enormous galaxies. So a galaxy is a collection of hundreds of billions of stars, and they're pretty localized, and maybe they're spirals and blobs, and they're very far away, and they're also moving away from us in every direction, which is very peculiar. So he makes this plot. It's completely freaky, but it gets freakier because the further away they are, the faster they're expanding away from us.
And they're calculating this all without computers.
Well,
hundreds of billions.
People were called computers back then.
Sure.
If you look at old dictionaries, look at the word computer. A person who makes calculations.
The person who computes. So.
Wait. And there's a room full of.
And yes, but they're doing it without the machines. With the
there's a room full of computers at Harvard at the time.
Yes, so he actually uses the work of one of the Harvard computers, which was a woman named Henrietta Leavitt, and she was part of a group of women who worked at the Harvard Observatory that were called Pickering.
And she talked like this.
Well, they were called Pickering's harem because Charles Pickering at one point was so frustrated with his male computers that he fired them all, and he said, my maid could do a better job, and he hired his maid, who was Wilhelmina Fleming, and she did a great job. And she hired all these other women, and one of whom was Henrietta Leavitt, and she made 30 cents an hour. Go, Henrietta.
Are we applauding her or her pay? That was weird.
30 cents an hour. That's
She should be making iPhones.
Okay, so.
I said it. I said it.
All right. So, but mixed in here, we've got simultaneous things going on. Einstein's general theory of relativity is already at the races. Okay, so that came in 1915. Okay, that gave us a mechanism to understand what the whole universe could be doing. That just catch us up on that.
Well, Einstein writes down his equations in 1915, and initially he applies them to things like the motion of the Earth around the sun and terrestrial and nearby local things. But then some other very creative thinkers, one in particular was a Belgian priest named Georges Lemaître. He decides to apply the mathematics not to something in the universe, but to the entirety of the universe, and find from the equations that the universe should be expanding over time. It should be swelling.
But just to be clear, he was able to do that not based on his training as a priest. He was a priest physicist.
He was a priest physicist, but no doubt his interest in applying these ideas to the entirety of the universe was not distinct from his focus on the big questions of existence. So they weren't that separate, although he, in his own mind, was very clear. He said there are two ways to have deep insight about the world. There's mathematics and there's salvation. And he said, let me follow both. And that's what he did.
But not intermingled.
He was very clear not to.
There was a line in the sand.
Absolutely.
Between the two.
Yeah.
Wait. So Lemaître.
I'll let you guys figure out the pronunciation.
So
he takes the equations. We have an expanding universe, but Lemaître
Before Hubble.
Lemaître predicts an expanding universe.
Yes.
Using Einstein's equations.
Yes.
So Einstein could have made the prediction and he didn't.
Yeah, in fact, in 1917, Einstein actually got there first. And when he applied the equations to the entirety of space, was very disturbed that he couldn't get a universe that met his own philosophical prejudice.
Which was?
That the universe is fixed, eternal, static, and unchanging.
Why would anybody think the universe could be anything other than that?
Well, I mean, there is this book called Genesis, which seems to suggest a beginning.
Okay.
So there are some people who think perhaps that vision is not correct, but Einstein and many others at the time very firmly believed that the universe could not change on the largest of scales.
And that's just a philosophical bias.
Totally. And in fact, he changes.
Wait. How could he get away with that if all the galaxies have gravity? And if they all feel each other's gravity, they would all collapse down into one point.
Yeah, so this was an argument that Isaac Newton actually gave hundreds of years earlier. But if the universe is infinitely big, and if the galaxies are spread across an infinity of space, then there is no center for them to collapse toward.
Got it.
So you can envision a static universe. Now,
if it's infinite.
If it's infinite.
If and only if
But
it's
even
infinite.
more than that, Einstein then, in his own general relativity, recognized basically the issue that you're raising in a finite universe. And he said, let me introduce a repulsive push to counter the attractive pull of gravity.
And anti-gravity.
An anti-gravity force field called the cosmological constant. So he introduces this into the math in 1917. It was not in the 1915 equations. He introduces it just to have a static universe that will allow him to breathe easy.
And to fulfill his philosophical bias.
Exactly.
Then Lemaître says, we can have an expanding universe. And so how did Einstein react to that?
Einstein learns of this from Lemaître in 1927. And he says to Lemaître, your calculations are correct, but your physics is abominable.
Oh, them fighting words.
We're fighting words. Wait, by which he was saying you can't trust that every mathematical calculation tells you something real about reality. Some math should be in math textbooks, and it's interesting, but it's nothing more than a mathematical curiosity. And he says, Lemaître, your idea of an expanding universe, that's a mathematical curiosity. It's not real.
Okay, so then 1929, Hubble discovers an expanding universe. Now what? What happens next?
Well, so it's interesting because the way I originally described it is kind of confusing. You might think it makes it seem like we're at the center of this expansion and everything's receding away from us. But the way the Hubble law is specifically, it's much more like the space between every galaxy is actually stretching. So from their point of view, if you were on one of those other galaxies, it would also look like everything's receding away from them. Right, everything's receding away from it. And if you imagine that it's not the galaxies literally moving on space-time, but actually the distance between the galaxies that's stretching, then something further away is actually moving away from you faster. There's more space stretching. And this was really closer to Lemaître's description. Not even closer, it simply wasn't static.
So just so I'm clear, at that time, they believe there's only one galaxy. In approximately 1925, just so I'm following. 'Cause I feel like I'm in a Chris Nolan movie right now. I'm watching Tenet. Let's pause real quick.
No. Up until at the time, 1923, 24,
one galaxy.
One galaxy. It wasn't
we are the
one
main
galaxy,
character.
It was one universe.
One universe. Copy.
Yes.
Here we are, 2025, from what I understand.
Yes.
Now there's
how many universes are we in now?
But are you talking island universes or are you talking universe?
I'm talking about the whole
Oh, good
thing.
God, there's one universe that we know about, filled with 100 billion galaxies, each of which has on the order of 100 billion stars. There are theoretical ideas that Neil is suggesting we might get to tomorrow that speak to the possibility that there might be other universes. So the answer is we don't know for sure, but the data seems to suggest that there's one universe.
Well, we were talking about this backstage.
Yes.
If the delta is that big between those two numbers, which is one and which you just basically said a gajillion, how do we know that what we're living in right now, the data that we know right now, isn't going to be wildly off and 50 years from now or 100 years from now, they'll be like, look at those dum-dums in 2025.
We hope that that's what will happen. That's what we live for.
So
we live to be
wrong.
Stupid.
Oh,
we live to be wrong. We're scientists.
oh, got it. We live to be wrong. We're got it. Okay.
Well, so let's follow through this reasoning. We discover an expanding universe. If we're expanding, that means we're bigger today than we were yesterday, and bigger yesterday than we were the day before. So logically, where does that take us?
Bigger?
No, going back in time. Where does that
Oh,
take us?
I'm sorry. So, yeah, so if you're already disturbed about the lack of permanence to the universe, then this very quickly leads you to have even greater existential dread, because if you run the movie backwards, then everything was once closer together. And if you keep running the movie backwards, it gets to a point which seems quite catastrophic, where these galaxies are literally on top of each other. And eventually, you're kind of imagining something that's so dense that you have to start thinking of it as hot and soupy and chaotic. And then what?
What did Lemaître call this?
Yeah, so Lemaître basically said, look, if the math is saying that the universe is expanding today, and if then Hubble's data shows that the universe is expanding today, just wind the cosmic film in reverse. You run the film backwards and things get closer and closer together, and there suggests that there's a point in the distant past when everything was on top of everything else, and he calls this the primeval atom. This is the beginning, according to his description.
Okay, and I happen to know there was an astronomer active at the time, very brilliant guy named Fred Hoyle, who was not into a universe that would be changing.
Yeah.
He knew the universe was expanding. He couldn't reason that away.
He accepted that.
Yeah, accepted that. But if you're expanding, but you're always the same, that must mean matter is being spontaneously created in the void to create new galaxies, so that statistically, the universe always looks the same.
Yeah.
But here's the thing. If the universe is expanding, that in itself is a change. So why would you not accept a changing universe?
Because he wanted to always look the same for all of time, for all eternity, in the past and in the future. And again, it's a philosophical bias.
But I think the idea of a beginning was particularly disturbing. The idea, so this primeval atom that Lemaître
Is
was
it
talking
disturbing to
about.
scientists, but not for religious people where God made the universe? They're perfectly happy with the beginning.
Look, Pope Pius XII, perhaps the nerdiest pope in history, who loved science.
Wait, why do you know this?
I don't know. He took Lemaître's work and he said, there is the scientific evidence for Genesis. That's what he said.
Oh.
And when Lemaître heard this, he threw a fit.
Belgian priest, Lemaître.
That's
the Pope
right.
is talking to him.
Not directly, but yes, when he catches wind that this is what the Pope is saying, and one of his students who was in the class that Lemaître had to teach that afternoon after learning it, said that Lemaître, who normally was very quiet and mild-mannered, he came in and ranted for 45 minutes because his whole point was, I am not blending my religious life and my scientific life, and here the Pope is taking my scientific work and he's turning it into religion.
But notice he said all that to a student and not the Pope.
You don't want another Galileo situation.
Exactly.
Yeah, so I have a tamer version of that quote. It's, as far as I see, such a theory of the primeval atom remains entirely outside any metaphysical or religious question.
Yeah, that's after I had a couple drinks and chilled.
Okay, so then it got called the Big Bang by
Fred Hoyle.
By Fred Hoyle.
Yeah, so Fred Hoyle was in a 1948 BBC radio interview.
Why do you know this level of detail about this? Okay.
And so he is describing his own approach, which, as you mentioned, is a steady state approach where matter is created spontaneously and fills in the gaps in space. And so they ask him about this other approach, not his. And he says, oh, that theory in which all matter must be created in one Big Bang. And that's where the idea of Big Bang theory comes from. Now, people have interpreted that as a derogatory description. His own way of recounting the story is he was simply trying to draw a distinction between a theory in which, in his steady state, only a little bit of matter is created here and there across space versus this other theory.
Like one hydrogen atom per century per cubic light year. I mean, there's some small rate
Not quite that small. So it is 1 atom per century per Olympic-sized swimming pool.
Oh, okay. I thought it was bigger than that. Okay.
And that's all that you need. And so it's kind of an amazing
in the whole
thing.
universe. Yeah.
Mm-hmm. Because what's more believable, that one little atom forms in a cubic, in a swimming pool-sized arena of space per century, or that there's this moment where everything is created all at once? Framing it that way, his theory sounds perhaps a little bit more believable.
Less crazy.
Yeah.
Yeah. So what do we have to assume if there is a Big Bang? So we got to assume that the expansion has been uniform the whole time.
Not necessarily.
No, it doesn't have to be uniform.
No?
Yeah, it can change over time.
Oh, that's been always expanding.
It's always expanding.
Okay.
Yeah.
And
Unless there's extra dimensions, those might.
All right. Well.
so it can expand differently in a
Brian
higher
and I are
dimension.
talking about this later. Well, yeah, you can squeeze into the other dimensions. There could have been chaotic mixing of the expansion and contraction, but overall, the overall volume of the universe was expanding.
But the way you get this is looking at the rate at which the universe is expanding.
Yes.
And that is a slope on a graph. And Hubble first derived that. And there's a slope. He called it the letter C, which is for constant. But since then, we swapped that out with a capital H for Hubble. And we call it the Hubble constant. Very famous Hubble constant.
So it's constant over space. I mean,
It's
not
important to
necessarily
realize
over time.
it's really the Hubble parameter, we should call it, because it does change in time.
It could have been faster in the early universe, faster in the future.
All right, so Hubble, he had the wrong, turned out the Cepheid variable he used, he didn't know at the time, there were 2 varieties of Cepheid variables, the one that's near us and the one that you can see from far away. And he presumed they were the same, no reason to think otherwise.
Right.
So he got the wrong distance, the wrong expansion rate of the universe.
So Cepheid is like diabetes. It's type 1 and type 2.
Yes, there's a type 1 and type 2. Exactly, I think.
Maybe not exactly.
Yes, there's literally type 1 Cepheid and type 2 Cepheid, and you got to use apples and apples when you're doing this exercise. So he got an age of the universe of 2 billion years. We would later refine these numbers. When I was in graduate school many moons ago, the uncertainty in the Hubble constant was a factor of 2. There was a 10. So with the Hubble constant, you run the film backwards, ask how much time at this expansion rate, looking backwards, when do we get to time 0?
That makes sense.
Well, yeah, just when is everybody in the same place at the same time? That's a perfectly sensible question.
Yeah.
And we got 2 numbers. There are 2 camps.
Okay.
A 10 billion year camp and a 20 billion year camp. A whole factor of 2. And everyone is, fighting for their thing. And we know they both can't be right. And so we need better data. One of the goals of
isn't being off by 10 billion quite a bit? That's a lot.
Okay.
Again, comedian, and I only took physics 1.
Okay.
In undergrad, I did not advance. I don't want the smoke, but I am saying being off by 10 billion is a lot.
Here's the thing.
Like if you go out to dinner and we split it, and I'm off by that big of a delta. If I'm 100% off.
Yes. Yes.
Aren't you you lose your science little thing?
No, so
you know what I mean? You've been disbarred. Yeah.
Here's the thing.
But you just get to talk your shit.
Here's the thing.
You are off by 10 billion. You get to talk your shit still.
Here's the thing.
Like my dad in the living room when he's giving his opinions about politics. He just gets to run his mouth continuously.
I got this.
Go ahead.
So,
this is a me and my dad thing, but I'm just a little mad that a capital S scientist was this off.
Okay.
Go ahead. And I have a second question, but go ahead.
The universe is vast.
Yes.
In time.
Yeah.
And in space.
Sure.
It is vast in every metric we've ever established for it. There are things that are vast in size, in temperature, in speed, in gravity. And so if I'm off by a factor of 2 between 10 billion and 20 billion, I could have been off by a factor of 10, by a factor of 1,000, by a factor of 1,000,000. We were quite happy we were in the same sandbox having that conversation.
So it's kind of like being Jeff Bezos. You know, if I'm off by 10 billion, not so bad.
So
can I also ask you the second philosophical question, which is no, this is for real. When you were like, it's either 10 billion or 20 billion, and I was asking you this backstage, which was, when the number is that big, is it almost like the United States' debt, where they're like, the deficit is at 28 trillion, and you're like, what does it even matter now?
Yeah, but
it's at a gajillion manillion. Like, what does it matter?
Well,
why does the number? Because I feel like a freshman in college.
When I'm done, it's going to matter an awful lot.
I would say that actually 10 billion is actually quite good. 10 to 20 is very much in the ballpark. Because
you should run the Federal Reserve. You should run it. Yeah.
This stage, who
Print
knows
more money.
who has access.
This is a good way to think about it.
You could have been off by $1 trillion.
Well, but the future is going to be much, much longer than the past. So it's not as though the universe kind of will expire within another 10 billion years, like we're confined to this number. The future could be just a huge number. We could be living in a time where it's not 10 billion.
But can I just give you perhaps one? These are all very, very good answers. But perhaps one other way of looking at
it. You're saying it was a bad question. Bad question. These are great answers. Bad question.
We don't care whether it's 10 billion or 20 billion. The number doesn't matter. What does matter is...
That's the most American answer, by the way. That's the most American answer.
Here.
Yeah.
The truth is we don't care, but we want our theories to work. We want our theories to make predictions that match with observations. That's the only thing that matters to us. The actual answer that comes out, whether it's 10 billion or 50 billion...
Or 42.
Like you're saying, it just doesn't matter. But we need to have a consistent description so that we have evidence that we know what we're doing, because evidence matters.
And both sides could not be right.
Right.
And so when the Hubble telescope was launched, okay, I'm just getting out of graduate school, it is launched. The number one goal set for that telescope was to resolve that discrepancy.
Yeah.
The telescope's named after the guy who gave us the Hubble constant in the first place.
Right.
Within 2 or 3 years, we nailed it. And the Hubble constant, its value would give us an age of the universe at about 14 billion years, which is comfortably between those two extremes. And that's science working at its best. It was, there's a limit to how much we can keep beating each other over the head. Let's get more data. Let's build a telescope that'll solve this.
And in fact, today, there is a similar argument happening. It's not between 20 billion and 10 billion, which, as you say, is a factor of 2 or 100% difference.
Yeah.
Now we're down to the 5% difference. We understand things that well that we have two groups that are 5% apart, describing a number of years, billions of years into the past, and that's the precision with which we can do it, within 5%.
And
do we
they
care?
will kill each other.
So again, we don't care the exact number.
Right.
We care that we can describe it with that level of precision when we're talking about events that happened billions of years ago. That's the mind-bending.
And here's the issue. When it was 10 and 20 billion, you always have to report your uncertainties for a number in science. And those uncertainties had a little bit of overlap in the middle. And it landed where you expected it to land. Now that we have two other warring factions on the value of the Hubble constant, those two numbers are within 5% of each other, but the uncertainties are tight. So the uncertainties don't overlap. And if you look at, go Google search on Hubble tension, and that's what will come up.
Adam Rees is coming to Pioneer Works in October. I just planted an ad.
Let me tell you.
Adam Rees, who's one of the Nobel Prize winners who discovered that the universe is not just expanding, the expansion's getting ever faster, it's accelerating, who is part of this Hubble tension debate, will be speaking at Pioneer Works on the Hubble tension.
Commercial.
Without waxing,
I dropped a commercial.
Without waxing philosophical, I just don't want to miss this point that we're not actually saying, which is what makes science so incredibly great is exactly what you all just demonstrated. It is this pursuit of the truth based upon the best available information at the time. So it's okay if it's wrong, because when it's right, we're going to get there.
Yes. You got it. All right, so we're turning the clock back, and we get to the Big Bang, but now the universe, large-scale universe described by general relativity, is now small. It is so small, you extend, the equations go back, the universe is the size of an atom. Does quantum physics apply to the entire universe or only to atoms? Where does that, where are you on that, both of you?
Well, at this point, we feel we have to invoke quantum mechanics to understand what was happening in the Big Bang. The energy scales are so dramatic, and that we're really probing quantum physics. High energies, you're really looking, somewhat surprisingly, at small scales. So we're still trying to grapple with what the Big Bang is telling us about the potential to understand not just general relativity, but a kind of quantum variant of that, if there is such a thing.
Yeah, so I got general relativity and I got quantum physics. Do they make nice in the sandbox?
It's a deep and difficult question, and one that I and many others have spent their lives trying to answer, and we do not fully have the answer yet.
Let me restate that.
Yeah.
That you and others have spent your lives failing to answer.
Yes.
Okay.
I agree.
That's
But I think we established
listen to this
that's
guy.
okay.
Yeah. You hear that? Take that.
Okay, you got a fan over here. All right, go.
No, it's exactly the case. So when you take Einstein's equations of the general theory of relativity and you try to invoke quantum mechanics within the same calculations, which, as you eloquently noted, you'd have to do. If you're talking about the whole universe when it's incredibly small, you need Einstein's general theory of relativity. It's the whole universe, after all. But you also need quantum physics because it is so small, and that's the theory that describes the small things. And when you try to simply put the equations together, you get one answer out from almost any calculation, which is infinity. And that might sound, oh, that's interesting, a big, deep, mystical number. No, it's nonsense. Infinity is nature's way of grabbing us by the lapel and slapping us around and saying, you're doing something wrong. You've got to figure this out.
So I've heard another one, that's where
do.
Infinity is where God divides by zero.
Yes.
Yeah.
Stephen Hawking, yes.
Yeah. Oh, Stephen Hawking said that.
Well, at least that's what he's attributed to.
Okay. Okay. But you're saying they don't make nice in the sandbox.
Yeah.
So there's a limit. What's this Planck length? What's going on there?
Well, the Planck length is the scale at which...
But named after who?
After Max Planck,
I love how you say Max.
I don't know. Is it? What do you think? Am I
I'd say
saying that
Max
wrong?
Planck.
I don't.
Max, okay.
Well, 100 years ago, in the early discoveries of quantum mechanics, was thinking about whether the universe was discrete or if it really was a continuum. And if I looked, for instance, at the air in this room, if I look closer and closer, do I find out it's actually made of individual molecules moving around and is not actually a continuum? And same with water. And was thinking about these things.
So in other words, water is not infinitely divisible. You get to the molecule at some point.
Eventually, you get to an individual quanta, a little particulate, a discrete bundle. And in thinking about this, there was sort of a fundamental scale that we would say is when we can definitely no longer think in a way where we're ignoring this quantum scale, where we're forced, as Brian's describing, beyond that, we're definitely going to strike an infinity, but by the Planck length, we're in trouble. We really should be trying to understand the theory of gravity at a quantum level. Maybe that means that space-time is coming in little individual bundles. I don't even know how to think about that. I'm just thinking about correlations between little tiny
Did you say space-time is coming?
Yeah, that was also wild.
Say that.
That was a wild sentence. I was like,
Yeah, that was very Game of Thrones.
space-time is coming.
Well, I mean, if it came from the Big Bang, I mean, was it the moment that space and time was in fact created? And are we thinking about things of a continuum of space-time itself?
Brian, how big is that smallest unit?
The Planck length is 10 to the minus 33 centimeters. And again, I know the question will be, well, how do you think about something that's so small? What does it matter if it's 10 to minus 33 or 10 to the minus 31? And again, we don't care about the exact value, but that's where the mathematics takes us. And just to get a feel for that, if you were to take an atom and, let's take a tree. Take a tree and expand it to be the size of the observable universe.
A tree.
Yes.
Tree.
Then the Planck scale, that 10 to the minus 33 centimeters, would expand roughly to the size of an atom. So the Planck scale is to an atom as a tree is to the universe. That's how tiny the distance we're talking about here.
And why? I'm going to channel
And so you measure
Hasan now.
this. You measure this with a ruler. What do you?
I know. I'm going to channel Hasan. Can I channel you right now?
You can channel me. I'm not going to even pretend like I understand what's happening right now. I'm going to be 100% honest. There's like 3,500 people here, and I'm like, don't act like you know. No.
I'm going to channel
You lost me at Space Time is Coming. And by the way, you came in quite hot, Brian, and you're like, I know what you're thinking. And that's not what I was thinking. I was thinking, I think it's really incredible. Let's just have a quick little tangent here. I think it's really incredible. It is almost 9 p.m., and this many people went on Ticketmaster.com. Paid fees, you way back there, up there, yes. Way up there, yeah. You guys paid tickets to learn about space nebulae. It was very heartening. So that's what I was thinking about, Brian.
Okay.
It's actually like, when people say this country's going to shit and math and science is at an all-time low, I'm like, you know what? It's the math and science lovers have filled up a Beacon Theater on a, of all things you could be doing at 9 p.m. Just
So I'm channeling Hasan here.
Sure.
Why do you have any confidence at all that you know what's happening on a scale that small?
We don't.
Oh, okay. That's the answer. That's the answer. Thank you. No, Chuck, come back.
Thank you. You guys. We don't know anything, and we could be off by a whole lot. Good night. Take care. Thank you, Beacon.
No. So let me see if I can unpack this.
Yeah.
Is it
Oh,
true?
we're going to figure it out right now.
Yeah.
We're going to do okay, sure.
Is it true that every prediction we've ever made with quantum physics, when we've been able to test it, has come true?
Absolutely.
Okay.
Well,
is it true that in
start.
general relativity, we already know what its boundaries are because there are calculations you cannot make because of this infinity problem?
Absolutely.
Therefore, if one of those is going to succumb to the other, it sounds like Einstein has to...
He's going to have to bow down to the quantum.
He's going to have to
That's what's
bow
happening.
to the quantum, bend the knee to
He's
the
going to
quantum.
bend the knee to the quantum.
So either quantum will absorb Einstein, or there's a higher level understanding that'll absorb them both.
I would say that's true, but also quantum isn't in competition. We have theories of matter, for instance, nuclear forces that we understand. They can be quantized, right? Theory of electromagnetism can be quantized. So there are laws of physics, and quantum mechanics is a regime in which we're understanding the highest energy attributes of those laws of physics. Now, gravity, Einstein's general relativity, is replace the theory of gravity with this theory of space-time, this theory of geometry.
Replace Newton's theory of gravity.
Replaces Newton's theory of gravity, but it is one of those forces. It should sit with the matter forces and have a classical regime, meaning a regime in which we don't have to worry about quantum mechanics, things look smooth, we understand general relativity works beautifully.
Regime sounds very political.
It does.
Dictator.
Totally does.
Dictator.
Dictated
Regime.
by-
It sounds very USSR. It sounds very
Unfortunately,
Kim
it's true
Jong-un-like.
everywhere.
Okay, got it. Okay.
But then when we go to the early universe, like the Big Bang or in the cores of black holes, where things start to get very extreme, we want to be able to quantize that law of physics.
As we have quantized other
It's not
things
going to
successfully.
replace gravity. Exactly. It's not going to replace gravity. We want to quantize gravity. And that seemed like a perfectly reasonable request.
And
Okay, so Einstein's equations are not quantized.
Yeah.
They require a continuum.
Yes.
So how do you quantize gravity?
Good. So Janna's describing the history is very insightful and useful. So we had an equation for electricity and magnetism that came from Maxwell. We were able to blend that with quantum mechanics, giving us quantum electrodynamics. It works. We had equations describing the strong and weak nuclear forces. We were able to embed quantum mechanics into those theories. Works wonderfully well. When we try to play exactly the same game with Einstein's theory of gravity, general relativity, and try to put quantum mechanics in there to quantize it, it just doesn't work. So what does that mean?
It means you're not smart enough to
Well, it's
figure it out?
interesting. It could be that we're not
Could be,
smart
yeah.
enough, and I'm full well willing to take that as the ultimate answer. But there's a lot of evidence, if you allow me to come right up till today for just a moment. I know you wanted to go
This is the
temporally.
centennial, but go
yeah,
on.
so there's evidence today that Einstein's general relativity, the reason why you can't quantize it, the reason why you can't put quantum mechanics into it, it already seems to have quantum mechanics embedded in a deep and subtle way that Einstein himself didn't recognize.
Oh, please do tell me, because my edible just kicked in, and this is fascinating. I mean, what you're saying right now is revolutionary, because what you're saying is you can't put something into something
if it's already
where the thing is there.
That's it.
We just don't know where it is inside of that thing, but once we find it in there, we're going to be like, yo, that's where it is. And be like, I told you not to put it in there. It was already in there.
Okay, Chuck
Amazing.
Chuck just blew a gasket. We gotta.
No, that's simple, it's elegant, it's profound, it's amazing.
I agree.
All right, so let's back up, back to the Roaring '20s, and I just want to go down the list of completely freaky things that quantum physics prescribed that defied anybody's common sense, and which is why it's still freaky. Mm-hmm. In fact, what's that quote from, was it Feynman about quantum physics? What did he say?
Yeah, there are a few, but if you think about quantum mechanics without getting dizzy, you haven't understood a single thing about it.
Oh, and I understand it very well.
Okay, so 1923, the wave-particle duality is proposed.
Yeah.
So that's kind of freaky. Mm-hmm. That particles are also waves.
Yeah, it was Prince Louis de Broglie who basically...
He was a prince?
He was a prince, yeah. And so he said, look, in 1905, Einstein showed us that light, which we had thought of as a wave, actually needs to be described as a particle, so-called photoelectric effect. That's how he went to Nobel Prize. 1905. Yes. And then in 1923, in his PhD thesis, Louis de Broglie says, let me do the reverse. Electrons, we always think about them as particles. Maybe they need to be thought of as waves.
Wow.
And that is a key moment in...
It wasn't his PhD thesis like...
That was a prince who did that?
A prince.
A prince? I don't believe it. I know current monarchy, not that intelligent. Let's be honest. Harry or William, you're not cooking this up. There's too much incest. I mean, you know this. You understand science. For you to be operating at that level. So, not buying it.
No.
You cheated off someone's paper. Not buying it.
So his PhD thesis, if I remember correctly, was like 12 pages long or something?
Yeah. Very short.
Very short.
Yeah.
And he got a Nobel Prize for that.
He got a 12-page PDF, and he got a Nobel Prize for a 12-page PhD paper.
Yeah. You said
let me just say, that's the smartest dude ever.
Well, that's how you know he was royalty. He turned in a 12-page
12
PhD
pages
paper.
and he took it.
They're like, Dr. Prince. And he's like, thank you. Double-spaced 12-page PhD paper. What a...
The tighter margin.
You entitled piece of shit.
A couple of years later...
sorry, Neil. I'm sorry, Neil. I shouldn't have spoken ill of the monarchs there.
No, that's this. I got nothing. This is America. We fought a war to get away from monarchs.
Not for long. Just give it time.
Okay. So then Schrodinger came around. Uh-huh. Oh, we have a Schrodinger fan up there.
That was the cat.
Yeah.
That was the cat.
That was the cat.
Cat. So what does Schrodinger do for us?
Well, Schrodinger begins to think more abstractly about what's real and what's not real. So we're used to thinking of particles. You've already described de Broglie and the electron. We think of these little fundamental particles almost like billiard balls acting out their lives, and they have some concrete existence. Schrodinger starts to say, well, this wave-particle duality, that's pretty profound, but maybe the only thing that's real is this thing called the wave function, which is the probability for the particle to be in a certain state, to be in a certain location, to be moving with a certain speed. But the particle itself, in some sense, isn't real anymore. If you look for it, sometimes you'll find it in a concrete location, but what is really determined by equations, by the laws of physics, is the wave function, which is this probabilistic description.
And the wave function occupies physical space, doesn't it?
Yeah, the wave function occupies physical space. It
Only
can tell you.
only for a single particle. So it's a kind of important subtlety.
Yeah.
For one particle, you can think about this wave function as filling space. If there are 2 particles, it lives in 6-dimensional space. If there are 3 particles, it's in 9-dimensional space.
Okay.
So you really can't think of it in these ordinary terms.
Ooh, I am high.
Wait. Okay. So if the particle can be anywhere here, and I have some barrier here, it could show up on the other side of the barrier.
Yeah.
Right, but it doesn't actually travel through. So let's say your barrier is a concrete wall. There's some small probability that you would find the particle. The wave function would describe the probability of finding the particle in this region of space, but it doesn't actually, like a billiard ball, travel through the cement wall.
Okay,
But
now this might be the THC talking, but the way you guys are talking, there might just be one particle. Like, there aren't a bunch of particles. It's just one particle.
I told you he blew a gasket.
Well, but Richard Feynman had the idea that maybe there was one particle that circled around through time and cycled back over and over again, giving what appear to be many particles now, but there's only a single particle through this temporal cycle. So you're right on target.
Moving forward and backwards through time.
Yep.
Oh, my God.
Okay. All right. So, but what I'm saying is, if a particle can show up on the other side of the barrier, then you guys came up with a word for that, and it's tunneling.
Quantum
It
tunnel.
can quantum tunnel through the barrier, but that's the point of Schrödinger saying what's real is just this probabilistic likelihood of finding the particle. The particle itself, in some sense, does not have concrete existence anymore.
Okay, so you know
it
what's
challenges the whole nature of reality.
No, but concretely, there is a probability that we could calculate
Yes.
for the likelihood of you tunneling through the stage and being underneath the floor. And it's a non-zero probability. It's kind of small, so it's unlikely to happen, but that's what quantum mechanics tells us.
But the smaller I get, the more likely it will happen.
Exactly.
It can happen in the laboratory.
Yeah, okay. So, just for context here.
Wow.
That is.
We were trying to understand how the sun made energy. And we did the calculation once we determined the sun is mostly hydrogen and it's hottest in the center. We said it must be undergoing fusion. And so, but you run the math. To undergo fusion, a proton, the nucleus of a hydrogen atom, has to merge with another proton, the nucleus of another hydrogen atom. Protons have the same charge. Electrostatically, like charges repel. So they have to be moving fast enough so that before they have a chance to repel, they stick together and form a new nucleus. Okay. We calculated what temperature that was necessary, because high temperatures give you higher speed. We calculated that temperature, and it was 100 million degrees, and there was no way the center of the sun was going to give us 100 million degrees, because you can calculate through sensible laws of thermodynamics what that should be, and we were scratching our heads. And then quantum physics comes around, and then you invent this spooky, magical thing called tunneling, and we discover in our calculations that at a mere 10 million degrees, see, this matters, 10 million, 100 million. Sure. At a mere 10 million degrees, they would otherwise not hit, but some of them tunnel through and connect. Tunneling makes the sun's energy production even possible.
Yep.
And I was like, because it's not just something that particle physicists worry about in their laboratory. I had to worry about it as an astrophysicist.
Why are you worried about this? It's okay.
Okay, thank you.
The sun's gonna sun, you know?
Yeah, thank
Tell
you.
Robbins, let the sun do that.
Thank you.
It's okay.
Okay,
We
got
need you, Neil. Don't blow.
Thank you.
gasket
That's
over.
very
Okay, so tunneling.
considerate
Tell us
of you.
more. There's a lot tunneling and yeah.
So now, what about the Heisenberg uncertainty principle? That seems like the biggest thing of them all. Talk me through that real fast.
Yeah, I would say so. That's the real moment when the old ways of looking at the world are shown they have to be jettisoned. Because the old way of looking at the world, what is reality? Reality is stuff that's at a location moving with a certain speed. That's the way we describe the world. And Heisenberg, with the armature of quantum mechanics, says you can't actually do that. You can't specify the location and the speed simultaneously of any object. You can't do it according to the quantum equation. So the very language of reality that we used to use
no longer
applies.
Why can't you measure both at the same time?
Well, if you have a particle described as a wave, right, and you want that particle to have a definite location, that wave has to be highly spiked so that you can say, almost 100% likelihood it's at this location. But when you see how the notion of velocity comes into quantum mechanics, it has to do with the wavelength of the wave. And so if you want something to have a definite speed, it has to have a definite wavelength. That's not spiky. So to have definite location, you need spike. To have definite speed, you need wave. Those are different shapes.
And you can't have them at the same time.
You can't have them at the same time.
Can I try an analogy nowhere near as precise as what Brian just said, but sometimes I like this musical analogy. If you play a chord, which is a whole bunch of notes together, you can play chords, but you can't simultaneously be playing a single note. So the chord is like a superposition of the notes. And how this relates is that when you're in a precise location, what Brian's describing as a sharp spike, you're sort of in a superposition of velocities or momenta. So it's like the location is the note, the velocities are the chords, or vice versa. If I know the velocity exactly and I'm playing chords, I'm no longer playing individual. I can't isolate a single individual note. I'm in a superposition of notes.
So how does all this connect to what they call the observer effect, where I want to measure the particle right there. I got to look at it, so I shine light on it, and the light sends it somewhere else.
Yeah.
So I can't actually ever know what the particle is doing.
Right. And so there's two things in there. One is, as you're saying, to look is to interact. And when you interact, say by bouncing a photon off a particle, you affect the particle.
Because I need the photon to take the picture.
That's right. So that's one key point that emerges from these ideas. But the other point...
So we can never know anything.
No.
Wait, don't leave on
that.
I've
Don't
started
leave on
here.
that.
That's the crazy thing. Y'all went on this crazy...
Hello. I'm sorry. I got that is just not right, okay? Quantum mechanics tells us that the things that you thought you could know are not the things that you can know. But with quantum mechanics, we've made predictions of the anomalous magnetic moment of the electron to 14 decimal places using a theoretical calculation, and we've measured it, and it agrees decimal by decimal by decimal on all of those numbers. And that's why we love these numbers. They show us that we understand what we're doing.
Okay, Brian just blew a gasket.
So you can know without knowing, is what you're saying.
We can know
Let me just say this,
things.
Brian. The type of energy you're bringing.
All right, wait.
Oh, man, you are built for CNN. This type of panel smoke. Oh, fantastic. Yeah.
All right, so
You should so be in one of those Street Fighter squares. The decimal to the decimal to the... Yeah, oh, it's great. This is great. This is good stuff. This is good television.
So...
Go ahead, Neil.
So this observer effect...
Bring us home with certainty.
...has been widely misapplied by people thinking my consciousness is affecting the measurement.
Look, there is a big mystery at the heart of quantum mechanics. Even with our capacity to make calculations that agree with observations to the level of precision that I just emphasized, perhaps with unnecessary theatricality, there is a question that we don't know how to answer, which is what you're asking. When you observe, you seem to be able to coax one result, one answer, even though the quantum description embodies many possibilities. We don't understand how that happens.
Is this the many worlds hypothesis?
It's one answer.
But the Schrodinger equation is so beautiful, and it does not actually include in it a way to understand how measurements are made.
Yes, that's the key point.
And so if you really take the Schrodinger equation very seriously, it simply says there are all of these possibilities, and they're all happening.
We don't have a theory of measurement to get us through
we still
where we are in the physics.
Just so you know, there are proposals. People have put down mathematical equations that do answer this question.
What is the many worlds hypothesis?
The many worlds hypothesis is if you have a description of a quantum system like a particle, and the quantum wave says 30% chance here, 20% chance here, 50% chance over here, when you measure it, you don't get only one result. There's one of you that finds it over here. There's another one of you that finds it over here. And there's a third one of you that finds it over here, but these are all in different universes.
Oh, it's Rick
That's
and Morty.
So you just invented multiple universes to explain something you can't otherwise explain.
The math invented it.
Thank you, Chuck.
Wait. That's really important. So this guy named Hugh Everett, in 1957 in Princeton, he studies the math, the very equation that Janna made reference to, the Schrodinger equation. He says to himself, let me take the math completely seriously and see where it takes me. And the math takes you, when you look at the paper, it's direct to this possibility of there being multiple universes. It's not made up. It really emerges directly from an analysis of the equations, and the equations make predictions that are confirmed. So you say, maybe I should take this math fully seriously, and that's where it takes you.
The passion with which Brian is describing this is like me explaining why I have glitter on my face when I come home because I was at an arts and craft fair.
Right. All right, we're gonna have to land this plane soon. Just briefly, I know you spent your career doing this, but just in 30 seconds, explain string theory.
Oh my God.
20 seconds. Does life have meaning? Go.
I only need 10.
Okay.
No, look, the old picture was that the fundamental constituents of matter were little dot-like particles. The string idea is that maybe they're little extended filaments. And why do we introduce this idea? When you introduce this idea, quantum mechanics and general relativity do play well in the sandbox.
So,
wow.
Okay.
And that was less than 30 seconds.
Whoa. All right. Okay. So what's in the future? So I know astrophysically, we don't know anything about dark matter. We don't know anything about dark energy. We shouldn't have even named them because we don't know enough about them to even name them.
And they should be called invisible.
They should be called Fred and Wilma, with no bias. Or faster than light. Time travel faster than light travel, before the Big Bang. Is what you're working on, or your peeps, does it address any of this? Will quantum mechanics take us to all the places we need?
Yeah, I mean, there's zero evidence that quantum mechanics has any cracks whatsoever. It's the only theory that we've written down in the history
It's the most
of science.
successful theory.
Most successful theory.
Ever.
And so
Which gives you confidence to believe crazy stuff that it predicts.
Exactly. And so we're pressing on, and ultimately we think putting general relativity and quantum mechanics, either because they're already born together or because they're blended together, will be the key to answering these questions. We're not there yet, but that's exactly where we're headed.
And why do you need these extra dimensions?
Well, Brian was describing string theory, which may or may not be true, but string theory actually requires extra dimensions for it to make sense, for the mathematics to allow gravity and matter and quantum mechanics to play nice together. But even without string theory, the idea that there are extra spatial dimensions is just kind of a natural extension when you start to think about space and time, and you start to take seriously Einstein's ideas. So now we're in the predicament where maybe those extra dimensions are harboring the dark energy. Maybe there's some explanation for the dark matter having to do with the extra dimensions. So now we can start to think of the extra dimensions as a dark sector that are harboring really the resolutions. Like, we're observing them already. We just don't have the direct connection to be certain.
So they're invisible in plain sight. Is that what you're saying?
Yeah, I mean, they're not literally visible, but maybe dark energy is a consequence of quantum energies, which is a paper Brian and I wrote many years ago.
Dark energy?
Dark energy, which is driving the universe to expand ever faster, which is something we observe.
It is also driving my administration.
I've got to land this plane.
Okay,
go
on.
Oh, well, just that we might be observing through something like dark energy indirect evidence of extra dimensions. We can't literally see into them, we can't point to them, we can't move around in them yet, but we are living with the consequences.
So these could be manifestations of these higher order phenomena in the universe.
Which is part of the motivation for
Makes-
thinking
makes
about them.
Perfect sense.
Thank you, Chuck.
All right, yeah, just wanted to put a button on that.
Quote from Einstein in his denial of quantum physics, in spite of him contributing so mightily to the field, you described the probabilistic nature, especially from Schrödinger's equation, and Einstein said, God does not play dice with the universe.
And Niels Bohr retorted, Einstein stopped telling God what to do.
You don't know if God needs to make some money real quick. You don't know that.
With the dice?
Yeah, I can see him down. Papa needs a new universe.
I like how back in the day scientists threw shade at each other very poetically. The way they, kind of shitposted was very the use of.
Well, we have good vocabulary to work with.
Great vivid language.
They still do it the same today. They do.
The way I'm going to land this plane is offer you a cosmic perspective, something that I'm prone to do when we're exposed to this much information. When I think of the 1920s, as a scientist, it may be the most consequential decade ever in the history of science, based on how it influenced our thought, the trajectory of our research that would follow. But I want to make a slightly different point. Before the 1920s, what are scientists doing? Well, they're doing sciencey things, right? In a lab, there's a chemical, or there's a material. Or
Erlenmeyer flask.
Yeah, flask, thank you. Yes, you flesh out the picture of your lab. Okay. Suppose it was the 1920s and you had a friend, a relative, or you were a politician, and you heard that someone is working on the structure of atoms and molecules. You'll say, why does that matter to anyone? I'm a carpenter. I just care that my wood atoms cut, or that they can be shined, or polished, or painted. Why does that matter to me? I'm making cars in an assembly line. Why does it matter to anybody? You're taking your brilliant intellect and applying it to something that nobody cares about except your cadre of people. But they will tell you, well, it's the foundations of matter. And they'll tell you, I don't care, you're using up national resources to do this. Well, what has happened every time we research the frontier of science, in basically every frontier of science, whatever it looks like when you're doing it, it's easy to say that'll never apply to anything. Why are you doing that? You wait a little while, they're clever engineers, clever other scientists. They see problems in the world and they see a possible solution. Do you realize today there is no creation, storage, and retrieval of digital information without an exploitation of the quantum? The IT revolution that is responsible for nearly half the GDP of the world at some level was birthed in that decade at a time when people are just exploring the edge of our understanding of the world. Yeah, it would take 50 years, longer than what is typical for an R&D project to show up as a household product. But all I can tell you is if you know anyone who says, we're doing too much science, or this science is not relevant to me, or I don't know why you're doing this, that doesn't sound like it makes sense. What you're doing is you're cutting out at the kneecaps the legs of a future waves of discovery that could transform civilization. Not only take us to where we might want to go, but possibly solve problems that we might have created for ourselves. So, there is nothing more short-sighted in this world than anybody running up and say we should do less science. Because every one of us in this room has been touched by it. And there's no greater demonstration of that than the science that unfolded in that decade, the 1920s. That's the quantum side of it. In the astrophysics side, that birthed our understanding of the beginning of the universe and how the sun makes its energy. We would then learn how the stars manufacture elements in their core. We would learn, take a few more decades, exploiting the quantum, applying to other realms of science. We would learn that the very ingredients of our bodies, the carbon, the oxygen, the nitrogen, the iron, are traceable to stars that underwent thermonuclear fusion following all the rules of quantum physics. And those stars exploded, scattered that enrichment across the galaxy, creating the environment, the chemical ingredients to make star systems with planets, and on some of those planets, life. So that era not only gave us our IT revolution, it gave us an awareness of ourselves that borders on the spiritual. And it's the fact that not only are we alive in this universe, because of our ingredients are traceable to stars, the universe is alive within us. And that is a cosmic perspective. This has been StarTalk, live from the Beekman Theater. This is like our 5th time at the Beacon Theater, 5th or 6th time, and you guys have been a marvelous audience for us. We love you all. Oh, no, thank you. But more than loving you all, we love the support you give for science, because there is no future of civilization without it. We might as well just move back to the cave. So, as always, Neil deGrasse Tyson here, thanking our panel. We've got Chuck Nice, Brian Greene, Janna Levin, Hasan Minhaj, Neil deGrasse Tyson, you're a personal astrophysicist, as always, bidding you to keep, 8 of you knew this, okay?
We're gonna do it one more time, come on. All right, here we go. What's the tagline? Let me just...
Okay. Neil deGrasse Tyson, your personal astrophysicist, bidding you to keep looking up.
Keep looking up. Here we go. Remember, he's going to go, Neil deGrasse has and remember, those 8 people, they cared. You guys all paid money, USD currency, a real number that we know, Brian. You know exactly how much you paid to those sharks at Ticketmaster. F them. Now, he's going to go, Neil deGrasse has to keep, and then you go, looking up. Here we go.
Neil deGrasse Tyson, your personal astrophysicist, bidding you all to keep looking up.
All
right.
Yes.